All right, it's time for us to get started. All right, the first thing that I wanted to go over is a question that I got on Friday that made me realize that I think the way that I described this process was slightly wrong, and I want to make sure that we have a total understanding of the DFA reduction process here. Everything that I had said should be correct with one small exception of you're checking here not for different finality after the first branch or the first separation of finality. You're looking for whether or not they have different equivalence classes. If the destinations have different equivalence classes, then you want to mark the pair as distinguishable. Before this had said different finality on the slide when I had meant different equivalence classes. And it seems like that might be the same thing, but there's an example in the homework where that starts to become not true. So if you think about it in terms of different finality, you will very quickly terminate the process and get the wrong answer. And if you think about it in terms of different equivalence classes, then you get the right answer. Does that make sense to people? How that's different and how that applies to the homework problem? Hopefully some of you had run into that before. Right, so that clarification. Then we had a last few problems that we were going over. So we are going to take a look at number 19 and get a little bit more experience with regular expressions. So 19A, regular expression for the following languages on ABC. And A says all strings containing exactly 2 A's. Actually, did we go over that? Yeah, we did, didn't we? We said the last 2 to go, I think. All strings containing no more than 3 A's. There was a question here. Can you tell us the difference between equivalence and finality? I'll go over that. If you understand it, you can get work on this, but I will also go over difference between equivalence and finality. So in the equivalence classes, we started out making different subsets of states. And I think for our example, we had Q0, Q1, and Q3 in one equivalence class, and we had Q2 and Q4 in one equivalence class. So we started this based on finality. So the initial set of equivalence classes that you want to produce are based on that. So these are your non-final states, and these are your final states. But when you're comparing and trying to figure out something like where do Q0 and Q1 end up, you're not necessarily going to look at the associated states finality. You're going to ask the question, are the states that they end up in on that character in different equivalence classes? And that starts out being the same question. But as soon as you discover that Q0 is in a different equivalence class, so we break it out into its own equivalence class, it's still non-final. So if something ends up in it, you would want to terminate it, saying that, hey, they end up in they have the same finality in their destination, when we really should be saying they have the different equivalence class. So all of these are not final, but once we remove Q0 from this set and something ends up, this doesn't actually happen in the practice problem that we saw, but it happens in the homework, where you end up saying, okay, well, maybe Q2 and Q4, one of them ends up in Q0, one of them ends up in Q3. That's not actually what happens, but if that were to happen, then they would both be non-final, but we moved Q0 down to this other equivalence class, and so they'd be in different equivalence classes, which would mean that the pair is distinguishable. Questions about that? All right, back to 19B.
There's a slide that has all the notations.
It's probably spread throughout but I would expect most of it's in the very first slide deck.
Yeah.
But, or do you mean just for regular expressions?
I think
Just about everything should either be in that first slide deck or in the regular expressions. So things we know, we can use lambda to represent nothing. We can use any character in the alphabet. We can use our operators. Plus, that stands for union. Dot for concatenation, or you can just leave them next to each other, and a superscript star for star closure. People tackling 19B. Is there any intuition out there about how we might construct a regular expression for this?
it's a bad answer, but it's like it works.
It may not be a bad answer. What do you have?
I have basically a chain of like B star, well.
Yeah, that's an English understanding of it, because the actual expression is
lambda 3 times with anything that can go in between. That's not A, essentially.
okay. So you're picking either. Yeah.
More than just A and B. So used to doing A and B.
Yeah.
It seems a little bit.
Yeah. So anything that's not an A. Except could they also be A's? No, because we have no more than 3 A's. So it's the position, there are 3 potential positions of A's. They could either be there or not be there, with everything that is B's or C's in between them. That seems like a reasonable place to start. You're targeting.
I'm not sure.
So Dominic, this was the answer you came up with?
Yes.
Any number of B's or C's, an optional A, any number of B's or C's, an optional A, any number of B's and C's, optional A, any number of B's and C's. So this represents the 3 possible places the A could be in a string. Kind of representing the first 3 occurrences of an A, and we don't support the placement of a 4th A. since there's no star closure around any of these A or lambdas. That seems reasonable to me as one intuitive way to do it. One other way you could do it is to try to figure out and break this down into cases of saying something like, all right, what does it look like if there are no A's? What does it look like if is one A? What does it look like if there are two A's? And what does it look like if there are three A's? This will be shorter than that, but this is an intuition that will lead you to an answer. So something that has no A's will just be B or C star. We can union that with all possible ways to make one A. So we could have B or C star A, B or C star. Union that with, we just need to write out 2 or 3 A's now. So very similar idea. This is significantly shorter, this is significantly longer, but different intuitions will lead you to different correct responses. All right, the challenge problem. C is definitely a challenge problem. So let's see if we can knock it out and get one. All strings that contain at least one occurrence of each symbol in the alphabet. So we need at least one A, at least one B, and at least one C. Be curious if anyone has a solution that is shorter than my very brute force solution to this. It's a disgusting brute force solution. Does it have an answer?
Fully stressed.
Hmm?
Mine is probably 40, I'm pretty sure.
It's,
It's,
yeah, yeah.
I wrote one part of it and then said, and then this, for every version.
Yes, that's probably what I will end up doing too, unless someone has a significantly nicer.
No.
Anyone have some logic behind this? How did you think about the problem to be able to come up with an answer?
I wrote out A, B, and C and then put. Every other option.
It's a good idea.
Before and after.
Unfortunately, that will only work if the A comes before the B and the B comes before the C. Yeah. So that's an excellent idea, and it solves 1/6 of the problem, and I think we need something that is 6 times longer for a brute force solution. So thinking about all of the possible combinations of the order that these 3 symbols could come in leads us down the, all right, well, we need cases for A, B, C, for A, C, B, for B, A, C, B, C, A, C, A, B, and C, B, A. Because they can appear in any order. So A, B, C, how do we do this? Well, since it is at least one occurrence, who knows what comes before the A? So we need to write out anything could come before the A. Then anything could come after the A, between the A and the B. And then anything could come before the C. And then anything could come after that. And that's just one of the possible combinations. So we need to union it with continuing this process. So the constants in this expression are always going to be the A or B or C star in all 4 of those locations. And then we're gonna map each one of these to A, B, C, A, C, B. So this represents part 1, this represents part 2. And it's what goes in between, it could be anything in the alphabet. And there will be 6 of these rows for the whole regular expression. Can anyone think of anything shorter? I racked my brain for 5 minutes and couldn't come up with anything shorter, but maybe one of you will.
So couldn't one, if you take away, if you just have the A plus B plus C and the A plus B plus C, couldn't that take care of B A C and C A B?
What do you mean? So you're saying in part 1,
Yeah,
if we had,
you just leave the first 2 expressions with the A in the middle. Would that take care of like 3 and 5?
okay. I kind of see what you mean. So we could have.
I mean,
What if we made this A optional? No, that won't work.
it has to be in the middle.
If the. Yeah, you're kind of right. We could chain these together and make the first and last of them optional. Kind of, so that the last one would represent an optional last character, so we would have like I don't know, I still think it wouldn't work.
Are we searching for like any string at all, or just those specific strings?
It's any string at all that contains at least one of each. We just have to be able to identify where that one of each comes from in the string. So if we had something like A followed by 10 Bs, we could identify the first A, we could identify the first B, we would not identify that C. So we would reject the string. So I think we need all 6 of these. I don't think there's an easy way to just combine these that I'm seeing. Doesn't mean it doesn't exist. But I did look it up and this is the book's answer as well. So I would think that if something shorter existed. Might have found it, maybe. All right, any questions about how to logic some of these regular expressions into existence? Interesting way to put it, but. All right. So this was our first kind of just break for some practice problems. We're going to go back to some content and we're actually going to spend quite a bit of time talking about grammars now. Talked very briefly 2 weeks ago about what a grammar is in general. And you did some homework problems that just had you looking at grammars in general. But now we want to specify, we're going to look for grammars that can produce the same kind of language that the DFAs and NFAs and regular expressions that we've seen so far can also generate. Since there's also an equivalence in grammars. And this becomes very useful when you're wanting to specify languages in different forms. Okay, so grammars, another way of specifying a regular language. So we're going to need to re-specify terminals and non-terminals. Terminals were those characters in the alphabet. So if the alphabet is A, B, C, like in the last problem, a lowercase a or b or c would be a terminal. A non-terminal is a variable that represents a more complex structure that needs to be further defined in terms of other non-terminals or terminals. And that way we make productions that allow us to specify levels of abstractness in the language. It's actually very similar to object-oriented programming, where we have primitive variables and then we have objects. The most basic objects are only composed of primitive variables, but it's also possible to compose objects out of other objects. So composition is it's very much like what the grammar is doing. Taking some very primitive constructs, the characters in the alphabet, and talking about how we can put those together in more complex forms. So a lot of the logic that you use in object-oriented programming, object construction, can also be used to help you design a grammar. Another thing to specify is all grammars break down into nothing but primitives by the time that you're analyzing whether or not a string is in the language, yes or no. So it would be the same thing as breaking down an object. An object is composed of other objects, composed of other objects, until you get down to primitives. All right, so regular grammars are going to have additional restrictions placed on them other than the rules that we've already learned about. And that's because regular languages are more specific than you can just generally put together with the rules in the grammar. So we're going to specify one of two ways we can construct a grammar as either right linear or left linear. So a right linear grammar has two possible production types. The first, the second, and we will define here that X is either a string, it has to be a string of terminals. And this B represents a single non-terminal. So this could be as many terminals as we want. Could be 10 terminals, could be 0 terminals. Well, 0 terminals wouldn't really make sense if you just take A out of the language completely and just specify the definition of B. But it can be any number of terminals with or without a non-terminal. But there can only be one non-terminal in each production. Questions on that concept? Does that intuitively make sense? Left linear is the exact opposite. If there's a non-terminal, it's gonna appear on the very left side of the string of terminals. So we cannot have a string of terminals, a non-terminal, and a string of terminals. We cannot place that non-terminal in the middle. It either has to go on the far right side or the far left side. And this has to be consistent across the entire grammar. If you have 10 productions, if it's a right linear grammar, all non-terminals are on the far right. If it's a left linear grammar, all non-terminals are on the far left. If you can construct either a right linear grammar or a left linear grammar, then the language you are trying to represent with that grammar is regular. If you cannot construct such a grammar, the language may not be regular. Here's an example. Is this grammar left linear or right linear? Or neither? Remember that whenever you have an or here, these stand for separate productions. So you could also draw this as this or B is not there, and you also define A to be B. So you can think of them as separate productions that each need to adhere to the left linear or right linear rules. So ors are allowed, they just are a shorthand.
Left linear.
Yeah, we have one person here and one person remotely saying this is left linear. What makes you say that?
Terminal, I believe, the A.
The non-terminal?
Or the non-terminal, yeah, that is on the left.
The
side.
variable, yeah. So the question about whether it's left linear or right linear is, where's the variable or where's the non-terminal? It's like, where's Waldo, but significantly easier. So if you have a regular grammar like this and you want to figure out how to derive a string from that grammar, this is one example where we say, all right, we're going to start with the start symbol S. We're going to substitute that S for the non-terminal A, followed by the terminals A, B. So we're doing that substitution. Then for this A, we're going to make that substitution. So does this make sense? How we're only expanding this A? We're replacing this A with the definition of the A, and this AB stays at the end. So we're breaking this into two parts, the definition that we expand and kind of the excess that we're carrying over from the last step. As we now change this A into this B, we're going to make the substitution of this A for this B, which is just the A to B rule right there. And then we substitute B for the terminal A. And we end up with no remaining non-terminals in the derivation. Once we do that, we're done. And the resulting string is in the language. Since this is left linear, we know that the language that this grammar accepts is regular. And one such string in that language is AAB. Questions on the derivation? Questions on the grammar? Another example, here are some productions. Left linear or right linear? Or neither? Either. Why?
Because there's not.
Yeah. Non-terminal over here on the right, non-terminal over here on the left. Once we define this grammar as left linear, all have to be left. This is not the case. Once we define it as right linear, all have to be on the right, which is not the case. So this is not a regular grammar. Even though this represents some language, that language does not need to be and probably is not regular. So the next thing we might care to do is we have a grammar. How do we construct an automata from that grammar? All right, so we're going to take the non-terminals and we're going to start representing them as states. So states representing each non-terminal. So we're going to turn the S, the A, the capital S, capital A, capital B into some subset of variables. So V sub 0 stands for the first variable, and here we're using variable and non-terminal interchangeably. You also want to add a final state here for when we reach a complete derivation, which we will do. You'll notice that there's, if we go from B1 and read a B, we end up in a final state. Because these lead to transitions to non-final states because there are still variables that need to be resolved. And then once we have a variable resolution like this, that will be a path to a final state. So the first production, at the very top, tells us there's some edge labeled A between V0 and V1, meaning that we consume an A and we get from V0 to V1. Right? Does that make sense? So we'll draw this out. We have V0, normally we label these Q0, but since they represent variables in a grammar, we'll call them V0. We consume an A, and we go to V1. If we were to do this production, we would have a start state, and we would end up, whatever comes after this comes after the A in the string, right? However we define V1 and expand that into being some other things, that A is guaranteed to be there, and this will be the case for all right linear grammars. You're going to consume this and end up there. If you have a left linear grammar, then you need a slightly different approach. So this is why right linear tends to be preferred if you have a choice, is it makes it a lot more intuitive to construct an automata out of it. First part of the second production tells us there's an edge labeled AB between V0 and V1, right? Since there can be any number of terminals here, there's an edge AB from V1 to V0. How do we make an edge labeled AB? That's not in our finite automata rules for two characters. So what could we do about it? Yeah, add an intermediate state. So we're going to draw a V2, and this transition will be an A, and this transition will be a V. Now, note this is not a total function. I can make this a total function at the end, but we may end up needing some of this as we go. The second part, I guess, okay, yeah, break them apart, add a new state in between, we did that. Second part of the second production, there's an edge labeled V between V1 and this VF, this final state that we're producing, saying that if we make that associated transition, we reach a final state. So from V1 to VF on a V. So definitely not a DFA, but is it an NFA? Yes, it is. We don't need to further specify. So it turns out that translating a right linear grammar into an NFA is actually quite straightforward. Question asks, how did we get from V1 to V2 consuming an A? So we need to consume both an A and a B here to get from V1 to V0. So we need somehow to get from V1 to V0, consuming an A and a B. There is no rule in an NFA that allows us to have an edge that consumes multiple characters. So we needed to create this intermediate state in order to break apart the AB into a transition that consumes the A and a transition that consumes the B. But it comes from this production of the grammar. So there's an NFA. This doesn't have the state labeled V2. Doesn't really matter what you label it, especially because it doesn't map to a variable in the grammar. So by calling it V2, I probably shouldn't do that. I should probably call it some kind of like intermediate I sub 0, I sub something. But yeah, notation can be a bit tricky. I would never penalize you for that, though. You can name your states whatever you want as long as you come up with the appropriate logic. All right, let's say we have a regular language specified in, maybe this is in regular expression form, or just A star A. How can we construct a regular grammar, given that we have this associated language? So the first thing to decide is we want a right linear grammar or a left linear grammar. We'll start with a right linear grammar, because I think this is going to be slightly easier and more intuitive to see. So we'll start with any constant characters on the left-hand side. What are those? What are the constant characters before the unknown? Or I guess what's unknown about this string? Or a string that represents this in this language. Yeah. How many B's? There could be 0, there could be 1, there could be 2. But what we know for sure is B's are constant. This is a question mark, this is constant. So if we're doing a right linear grammar, then the variable needs to be on the right-hand side. So what we're going to do is we're going to specify this whole thing kind of as the question mark, or as the variable in this. Because we cannot make a production that has a non-terminal in the middle of some terminals. So even though there's a constant on this end, we're not going to specify it yet. We're going to instead take all the constants on the left-hand side and turn this into a production. So we're going to say S leads to A, capital A. And this capital A will eventually figure out the B star A. So find all the constants. For star closure, like B star, we can use the concept of self-reference. What that means is we're going to have a non-terminal that comes back to itself. It's like recursion. So this allows you to say, all right, our A can either have a B and then go back to A, where we can continue to make B's in front of A, B in front of A, B in front of A, looping that as many times as we want to. Before, we have a single non-terminal, B, that can represent the closing A. Now, granted, we don't necessarily have to include that B there. This could just be an A, and we remove B completely from this. Both of those are equivalent grammars, both of them are correct. So this represents that. This represents that. And this represents that. So whenever you see star closure, there's going to be self-reference in a production and a grammar. Questions on this? Does that make intuitive sense? As we come up with more and more complicated regular languages, we're going to use transitions of some kind of equivalent DFA or NFA to show that we can produce the grammar. It's much easier to go from a DFA or an NFA to a grammar than it is to go from a regular expression, so you may need to use that as a middle ground. This is about as complicated as regular grammars get, which is incredibly nice. They're not super complicated. You just have to remember to construct something that's either right linear or left linear, and the way that you're going to do that is kind of chunking out the either constants or variables. And if that variable represents star closure, then you'll have self-reference in the grammar. That's it. That was an entire sequence of slides on a topic. Regular grammars are very nice and easy as long as you've already studied DFA and NFAs. You can transition to and from them relatively easily algorithmically. We will be seeing some things that are not as easy algorithmically in the fairly near future. That will make you remember the good old days of regular grammars. One of them we'll be talking about starting right now. Has anyone heard of the pumping lemma before? Or know what I mean by the pumping lemma? It's something that every student who goes through this hates for a while until they understand it, and then they still hate it. It's one of the harder topics in the course, but it's a very necessary topic because there's one big gaping hole in what we haven't talked about in terms of regular languages. Does anyone know what that intellectual hole is? We've shown over and over and over again how we can construct regular languages and represent regular languages. What haven't we done? So we've shown how to show that a language is regular. We can do that in one of four ways. Construct a DFA, construct an NFA, construct a regular grammar, or find a regular expression. You can do any of those things, the language is regular. I think people at this point might see where we're going. How do we show that a language is not regular? We talked about what regular means. So if there's, I made this before we talked about that. So maybe there's a little bit of overlap here between the concept of, well, we need no memory in our control unit to be able to parse a regular language. We're going to go between some number of states. Those number of states are finite because it's a finite state machine. We don't need any extra memory as we do those transitions. So with a very limited amount of memory, we can accept or reject a language that is regular. Let's say we come upon a language and we need to know whether or not we need memory for it. Do we need to allocate a bunch of memory to potentially be able to accept or reject strings in this language? So I'll go over the refresher. We probably won't get started on the algorithmic part of this, but who remembers the pigeonhole principle from discrete math? Hopefully, at least people went over it. So we have n objects. We want to put them into k boxes. If the number of objects we have is more than the number of boxes that we have, then at least one box has to have more than one object in it. Does that make intuitive sense? I have 5 objects and 3 boxes. One of those boxes has to have at least one object in it, at least 2 objects. Either a box has 3 objects in it, or 2 boxes have 2 objects in it. There's no other way to distribute those 5 objects among those 3 boxes. One box contains at least the ceiling of n over k objects. Now, if I have 7 objects and 3 boxes, now at least one box has 3 objects in it. Because the ceiling of 7 over 3, 2 point something, the ceiling of 2 point something is 3. There must be at least 3 objects in one of the boxes. Some examples. For some reason, every example out there uses socks for this. You have socks that are red, green, or blue. I wish, right? How many socks do you need to pull out of the dryer at random to guarantee you have a pair? Knowing that we dry things and then match them. So I would need a pair of socks today. I have red, green, and blue socks. How many socks do I need to pull out to know for sure that I have a pair? 4. In the worst case, we pull out one that's red, one that's green, one that's blue. The 4th one we pull out has to be either red or green or blue, so it guarantees a match. How many people do you need in a room to ensure at least 2 of them have the same birth month? That would be the same birthday.
Oh, it's a month.
Month. Number of months plus 1. You have 12 people in the room, they can each have a different birth month. As soon as you introduce a 13th person, they have to share a birth month with one of the 12 people in there. There's no other possibility for them to select. How about at least 5 people sharing the same birth month?
Okay.
That's right. How do we get 49?
12 times 4 plus 1.
Yeah, if we assume that 1 year is distributed like this in an array. There's the 12. And then we do this and duplicate it 3 times. This would be the most people you could shove into a room where no more than 4 of them could share the same birth month. You have 4 of them, 4 in January, 4 in February, 4 in March, April, May, etc. And we need 1 more person to be that person that is the 5th person for one of these months. So we end up with an expression like 4 times 12 plus 1. All right, we are out of time for the day. We will come back with the rest of the preliminaries and start talking about the public level tomorrow. Remember that you have an assignment due on Wednesday. I have some office hours. I can help you out with that now. There is also a study guide for an exam on Friday posted to Canvas. Take a look at that and I can answer any questions you have about that, either in office hours or at the start of class starting tomorrow.
Yeah. I don't think we're doing this, but. So the people don't know, okay. I'm gonna be honest, yes, you guys.